All right, we are now recording. So,
Wizard over here. Can you move it closer?
all right.
Yeah. Can you see it?
All right, can everyone see the
Yeah,
page 231?
yeah.
Okay, I'm looking at right in the middle of the page, definition. Increasing, decreasing, and constant functions. You see the definition?
Yeah.
Okay, so keeping it simple without actually looking at any fancy notation. So let's just say here we have some, what probably is a polynomial function. Where a function is basically just like you read a book, as you are going left to right, as you see that graph move up, we say the function is increasing on that interval. And then here I hit what's called a turning point, kind of the top here. And from there, let's say from here to about what right here, function is what moving what down. And we say there we're decreasing. And then here would be increasing again to about right there. And then we would be decreasing. Constant means simply this. Let's say I was increasing here. Do I hit this point? You recognize a constant interval because you just have a flat horizontal line. Every output, every y coordinate is the same along that horizontal line or horizontal part of the graph. And that would be from here to here, what we call a constant interval. So when we identify intervals where we are increasing for a function or decreasing or constant, we always give it in terms of x. Right? If you look at the bottom of page 231, they draw out and then correlate with the definition and showing how that definition fits with the idea of, okay, if we're increasing for any two values within an interval, x of 1, x of 2, x of 1 being less than x of 2, your functional value of f of x of 1 is going to be less than f of x of 2, which is going to, that gives you the outputs are increasing on that interval. So that's just notation. What I want to before we get to that one, turn to page 232. And I'm probably going a little quicker than I normally would, but we're on the clock since we've got to get done by 10:29. So go to page 232. Just flip the page. And there are arrows at the bottom that you can just turn a page once.
I don't know.
Or you can just type it in.
I'm going to 232. Ah, yeah, that's what I missed on. Okay, yeah. Okay, we're good now.
Got it?
Yeah.
Okay, so you see there at the bottom, you've got definitions for local maximum or local minimum. Now, the word local, literally just think of it in the neighborhood, but you have some interval. Let's say we were looking at this graph right here. So this just interval of x values from here to here. This y value, the output would be the largest output in this neighborhood. This one, somewhere about right here, would be the largest output in this neighborhood. But it has to be within an interval so that if you had a graph of a function and it just went from this point up to this point, that y value I would not call a local. Now we'll give it another name, but it's not in a neighborhood. It's at basically at an endpoint. So it has to be within an open interval of values. And importantly, when you say, there are two ways to basically express this. What is the local max or local min, and where does it occur? The where is the x coordinate. what it is the y coordinate. So it's a singular value. At the top of page 232, do you see that little graph? It's figure 24.
Yeah.
Okay. So what I'm going to do, we're going to look at that graph, figure 24. I'm not going to draw the graph, but so for reference, we were on looking at this figure 24 on page 232. And what I'm going to do is write down increasing intervals. And how would I write them down for that figure? So I'm looking at this, and this function, again, remember, this is interval notation. Now, the book and I are going to have a little disagreement. They like to use brackets, which is including the endpoint. I don't. I use parentheses. It doesn't make any sense to say at one singular point you're increasing and decreasing if you have that value in two different intervals. And you'll be okay with the homework just using parentheses. But I would say I'm increasing from -4, where x is -4, over to where x is 0. So again, this is not an order pair, it's interval notation. It's all numbers between -4 and 0. But can you follow along? Just move horizontally and see what I'm talking about. From x is -4 over to 0, the graph is always moving up.
Yeah.
Does it make sense?
Yes.
Okay. And from constant interval would be going from where x is 0 over to where x is 3. And you can see that flat horizontal line, you're getting an output of 4 every single time. And decreasing, and this would actually be intervals, you'd be decreasing from -6 to what, -4. And you would also be decreasing from 3 to where x is 6. I could also say I have a local minimum at where x is -4, and the local min is -2. And that is it in this case. Now, another term, and it's on the next page, but we're going to keep looking at this graph. Absolute max, absolute min. And this would, when we say what is the absolute max, it is the largest functional output a function can have. So that if an absolute min would be the smallest output you could have. So on this function of figure 24, where I had that local min at -4, and the local min was -2, based on that graph for that function, -2 would be an absolute min. 4 would be an absolute max, occurring, well, a whole bunch of times because it's at a part of constant interval, though that was not a local max up there because it was not in an interval, but it would be definitely the largest output based on that graph. All right, so now that we kind of have those definitions in hand, I want to go back to page 238. And on page 238, at the top, you'll see a graph on the right of the page, and I'm looking specifically at problems 13 through 24, all relative to that graph. All right, so we're just going to go through and answer these questions real quick, 13 through 24, based on this graph. All right, so if everybody's looking at it, first question on number 13 is a yes or no. Is the function is it increasing on the interval from -8 to -2?
Yes.
It sure is. So, yes. Give me a second. My dog is hollering to go outside and I don't want to have a disaster upstairs. I'll be right back.
Okay. He's so funny.
Okay. 14, is it decreasing on the interval from -8 to -4?
No.
No.
It is not. 15, is it increasing on the interval from -2 to 6?
No.
Mm, No, again. Is it decreasing on the interval from x is 2 to x is 5?
Yeah.
Okay. Now, 17. We want to list the intervals where we're increasing. So looking at that graph, I would say from what, -8 to -2.
Yeah.
The graph is moving up. It is also moving up from
0
Two.
to.
0 to 2. And also one other interval, and that would be what?
5 to 7.
5 to 7. Absolutely. Okay. 18, now we're going to list the interval or intervals where we're decreasing. So first one would be
Oh, 10 to
-10 to
Eight.
-8. Also -2 to
Oh, that's
0.
6.
Yeah.
And then from 2 to what?
5.
5. All right. All right. So 19. Is there a local maximum at 2?
Yeah.
And the answer is
Yes.
yes. So if you just go to where x is 2, you definitely have a high point right there in that neighborhood. So yes, there is a local maximum. Now, what is it? What is the local maximum value?
I think
10.
10.
Did you say 10?
Yeah.
Yep, that's it. Local max is 10. Okay. Now, we'll also turn out it as an absolute max. But 20, is there a local maximum at 5?
No.
No.
No, it's a local min there, not a local max. Okay. 21. I want to list the number or numbers at which f has a local maximum, and then what are those local maximum values? So that is, I want every x value where a local max occurs. So what would they be?
-2.
-2,
Positive 2.
+2, and that's it. Now, it's then what it says, what are those local maximum values? You would have in one case, what, 6? That corresponds to the -2, and you have local, we already knew, local max of 10. All right, let's do the same thing for local mins. Every x value where a local min occurs.
So -8.
-8,
5.
5, I'll agree. Any others?
Is
0?
0 one?
0, yep. Then what are they? You've got -4, you've got 0, and the other one is what? 0. So you have 2 local minimum values occurring twice here. Then it's 23 and 24. what is the absolute minimum on the interval from -10 clear over to 7. So your local, or excuse me, your absolute minimum value, the smallest functional output is -4. And then what is your absolute max? This would be 24. The largest output I see is 10. Good?
Yeah.
Good.
Yeah.
Okay. All right, one last thing in this section. That you will have to do average rate of change. Okay. Now, average rate of change. So abbreviate average rate of change is simply a slope. So if you have a function, you want to find the average rate of change from one X value to another X value. Oh, that's awful. So let's say I wanted to find average rate of change from a value A over to a value B. Then the ordered pair point would be A and its functional value F of A. And the ordered pair point here would be B and its functional value F of B. And I'm going to attempt to draw a line. And simply put, the average rate of change from A to B is simply the slope of the line, or what we call the secant line, which is connecting up these 2 points. So, or what we call slope, or change of Y over change of X. So your change of Y would just be F of B minus F of A. And then in same order, change of X, B minus A. And so if I were to say, take a function F of X equal to 3x squared. And I said, find the average rate of change. Find the average rate change from, let's say, 1 to 3. So these are understood to be the X values. So the average rate of change here would simply be F of 3 minus F of 1 all over 3 minus 1. So F of 3, if I plugged in 3 here, I'm going to get 27. F of 1, I'm going to get 3. And then the bottom, of course, you still have 3 minus 1. So that's going to end up being what? 24 in the top, 2 in the bottom, or at the end of the day, your average rate of change from X is 3 or X is 1 to 3 is 12. Now, if you picked another set of X values here for this function, you're going to get a different average rate of change. The only one that stays constant, the only kind of function where it's that average rate of change is always the same, is a linear function. That is a line, just because the slope is constant. So any issues with that? Seem pretty reasonable. Okay. So that was the fly by night of 3.3. So I've already assigned 3.3. It's got a due date of 3/15, which is, excuse me, next Tuesday. In your now we have the e-text or the e-text up there. I want you to turn to page where? Page 242, actually. Let's go to page 244. This is going to be in 3.4. And on page 244, go down a little bit on the page and you see where it starts constant function.
Yeah.
Okay. So what they are, and this section here is one of the titles of it is library of functions. I refer to these as parent functions. When we meet again on Thursday of next week, we're going to cover 3.5, which talks about transformations of functions. So as an example, if you go through, and I'm going to want you just to go through and look at each one of these, and there's about 8 of them. And they cover 244, 245, and 246, the last one called the greatest integer function. These are the base root functions. So as an example, one of them is absolute value of x, whose basic graph looks like a letter V, like that. And after we've covered 3.5, if I have a function that looks like, I'm making up something here. So let's say negative 2/3 times the absolute value of 4 times the quantity x minus 2 and plus 5. We're going to learn all these numbers have meanings in terms of taking this graph right here, this parent function, and stretching it, compressing it vertically, stretching it, or compressing it horizontally, or flipping it across an axis, either x-axis or y-axis, and then shifting left, right, or up, down. And what we'll learn is this negative sign indicates what I call flipping the graph, or a reflection across the x-axis. The 2/3 out here is going to be a vertical compression by a factor of 2/3. The 4 multiplied inside the function is actually going to be what we call compression of the graph, but horizontally by a factor of 1/4. This -2 here moves the graph to the right 2 units, and the 5 moves it up. And then, so that was a lot to say there, but we're going to cover all those transformations individually on Thursday of next week. And then we're going to hit them on these basic graphs, these parent functions. So all I really want you to do is, one, go through the text and look at each graph and start to associate that image of the parent function with, y equals x cubed, y equals square root of x, y equals cube root of x, y equals 1/x, so on and so forth. And also within this section is graphing what are called piecewise functions. Have you ever looked at graphing a function that looks like f of x equals x plus 1 if x is less than 0? Graph 5 if x equals 0, and graph 3x plus 2 if x is greater than 0. Have you ever graphed something that looks like that?
No.
Okay. Well, this is called a piecewise function, because it's coming in pieces. Now, it's still a function, so the same rule applies. One thing in, only one output. And what these are telling you is, if you put a negative number, you evaluate its functional value by using x plus 1. If you put in 0, you get an output of 5. If you put a positive number in, you use this. And you graph it literally in pieces. So up to here, you're graphing the line x plus 1. That's a slope of 1, y-intercept of 1, and an x-intercept of -1. And I would make this a open. It's up to, but not including that. Now that is just this piece. If x is 0, you get the singular point of 0, 5. And then this, from here on, you're graphing the line 3x plus 2. So it's a y-intercept of 2 and a slope of 3. So it's kind of, you just do that. And that's the quick version of how to graph a piecewise function. But you graph, so it's all one graph, but you're graphing kind of each one of these individually along the specified values of x. So I'm going to assign 3.4 as well, and work with as best you can. The lot of it is very easy, just going over those parent functions, and then there's a few piecewise functions to graph. So I'm going to change the due dates of 3/3 to the 17th. That's when we meet again, and also on 3/4. And then I will also send out a video link to problem number, it was either 12 or 13. I can't remember which, but it's the projectile motion problem using the calculator. So I can work through how to use the functions in the calculator to do that problem. And all right, so any questions before I let you go?
No.
I don't think so.
Okay. All right, so you guys talk with me. Actually clear this out. The two that are in calculus, do you talk to them regularly?
Yeah.
Okay, because so you let them know kind of what's going on, what's up here for the next week, and so on and so forth. I appreciate it. All right, guys, have a great day, and I'll see you a week from today.
Thanks.
See ya.
See you
Yeah.
guys.